Okay, so this may be a kind of a bit shorter lecture, but uh, here we go. Uh, so last time we uh, looked at the bound orbits around point mass, and in that study we saw that the orbit is elliptical, but the azimuthal angle after single revolution doesn't come back to itself. In fact, what we find is that the delta phi, uh, that value should have been 2 pi for it to come back to itself. It is not that, but it is 2 pi plus some additional number. And that number, of course, depends on the eccentricity of the orbit, in the sense that, like, whatever is the rho plus and rho minus value, these are the quantities which are related to the eccentricity of the elliptical orbit. and and because this number is non-zero and this thing and of course positive, the uh, after single revolution, the orbit actually has gone little further ahead compared to what it was where it started uh, uh, in the previous revolution. So of course the particle would come back to itself after uh, several revolutions, so that 3 gm of times 1 over rho plus 1 over rho minus times some number n is equal to 2 pi. So that just tells you that that number should be equal to 2 by 3 times rho plus rho minus upon gm times rho plus rho minus. That many revolutions would bring the orbit back to itself. Okay. Now, it is not guaranteed that this number is an integer. Okay. So if it is not an integer, then it would come close, but not to the same point, and then again it would continue. And of course, sufficient large integer number multiplying this would make this quantity integer, and therefore the real number of revolutions required for the particle to come back to its original position is this number times some other integer. Okay. He also said at that time that, like, if you substitute the original particle which generated the gravitational field mass of that particle to be the mass of the sun, then this perihelion precession factor for Mercury can be computed, and at least for Mercury it is measurable, and it has been measured, and it agrees with the computations that we have done. Okay. Fine. So there is just small comment that this result we have used we have done this computation in one particular coordinate system, but this is a physical observable, so therefore it shouldn't be dependent on any choice of coordinates, because anything which depends on choice of coordinates is not a physical observable quantity. Okay, so in that sense, it doesn't matter what coordinate system you use, you should get the answer uh, for the precision of the orbit to be 3 gm upon times 1 over rho plus 1 over rho minus. Okay, so let's consider gravitational redshift. This is another effect due to gravity, and uh, and one can see that this is in fact an effect which is a consequence of the equivalence principle. Okay, now to understand that, let's first understand what the equivalence principle is trying to say. The equivalence principle says that the laws of special relativity are applicable in the neighborhood of every ordinary point in the curved space. Okay, so unless you are kind of going to a point which is singular, like, a point where the curvature diverge or something like that, if you don't look at points of that kind, then the equivalence principle says that in the sufficiently small neighborhood of that point, the laws of special relativity should be applicable. Okay, so therefore, locally we cannot really distinguish between curved space and the flat space. Okay, so if you want to apply any rules only locally, you might as well work with special relativity. Okay, fine. So what we could try to do is to ask, how do the clocks tick at different points in the curved space. Okay, so the proper time is of course given by d tau square is equal to g alpha beta dx alpha dx beta, and uh, and if you are looking at time lag paths, okay, then for our choice of signature, time lag paths would require d tau square to be negative. Okay, so let's define some new quantity d tau prime, which is minus g alpha beta dx alpha dx beta. Okay, and then this would tell us that g alpha beta dx alpha by d tau prime dx beta by d tau prime equals minus 1. This is just rearrangement of this equation. Now, suppose we consider that a particle is at rest, then its spatial components of velocity vanish. Okay, and in that case, this equation becomes simpler, which is just g00 times dx0 upon d tau prime whole squared equals minus 1. Okay, so that tells us the relation between the uh, coordinate time and the proper time. Okay, that is that dx naught is equal to 1 over square root of g00 times d tau prime. Okay. Okay. So okay. So let's look at the behavior of how the coordinate times would click if we hold the proper time to be fixed. Okay. So suppose we look at the proper time to be say 1 second. Okay. Then in any locally inertial frame, the proper time would have the same value no matter what choice of frame that you have, what choice of coordinate system you have, and so on. Okay, then the coordinate time by looking at this equation would tell you that delta x naught would be 1 second times 1 over square root of minus g00. Okay, so that is this expression. Okay, so if minus g00 to the minus half is less than 1, then of course the clock will move slow, because if this quantity is less than 1, then 1 second proper time is less than 1 second in the coordinate time. Okay. Similarly, if minus g00 to the minus half is greater than 1, then 1 second in proper time is larger time in the coordinate time. Okay. But the point is that this information is not sufficient, because or is not measurable, because if this is true, if the clock is moving slower, then everything is going to move slower. If the clock is moving faster, then everything is going to move faster. Okay, so there is no way of detecting this kind of effect. The kind of effect that we can detect is ask what happens to the clock at one location versus what happens to the clock at some other location. Okay, so to do that, what we need to do is to probably try sending a signal from point A to point B. Okay, and the person at point A, the observer at point A, knows what signal has been sent. By that I mean what is the frequency of the light emitted, and that person can ask the observer at point B as to what is the frequency of light he or she has measured. Okay, that's the kind of experiment we can actually perform. Okay, so that is what we want to do. So we can detect the rate at which the clocks tick at different points in space-time with different values of g naught naught at different locations. Okay, so to do that, let's kind of take simpler case. It's not necessary, but but for illustration, it is simpler. Okay, and that is to take the metric to be static. That this metric has no explicit time dependence. Okay, so therefore, the the coordinate time intervals defined at the location of observer A and at the location of observer B would be same. Okay, because the delta t or delta x naught, okay, uh, wouldn't care about, like, uh, how the time is clicking. Okay, so I should kind of qualify this statement a little bit. This is not the correct representative of what I want to say. The What I mean is the following: that if the metric is static, then the delta t time interval. Suppose you look at proper time. Okay, so suppose you stay at point A. Okay, and for the coordinate time interval delta t, you want to ask what is the proper time. Okay, that proper time is same no matter when you do this measurement. Okay, so delta t is measured from time t1 or t1 to t1 plus delta t1 or delta t, sorry, or at time t2 and t2 plus delta t. Okay, because the metric is independent of time, the proper time at the location of the observer, okay, would be same for the same coordinate time interval delta t. Okay, similarly, the proper time at the observer B would be the same for the same coordinate time interval delta t. Okay, no matter at what time you look at the time interval delta t. Okay, fine. So suppose we have two observers and they are, of course, at different radial positions. So let's call them at RA and RB. Okay, then if we ask the observer A to send out a light uh, with a frequency say omega A, and ask the observer B to detect it. Okay, so the observer B receives this light, and the observer B kind of detects and finds that it has a frequency omega B. Then the omega A upon omega B, okay, that ratio is actually square root of minus G00 at RB upon square root of minus G00 at RA. Okay, so let's see how we get this expression. Okay, so this is a claim. We'll see how we arrive at this result. Okay, now suppose we keep the coordinate time fixed. Okay, so suppose delta TA is equal to delta TB. Okay, so that is possible simply because G00 is time independent. So therefore, coordinate time that you kind of measure here and coordinate time you measure at location B can still be same without worrying about anything. Okay. Then for a radial ray, okay, that means there is no angular dependence on the trajectory of the light ray. Okay, minus G00 times dt squared is equal to GRR times dr squared. Okay, because the total d tau squared should be 0. We are looking at the light ray. That tells us that dt by dr is equal to plus or minus uh, GRR upon G00 to the half. Okay. Maybe I should have put a minus sign here. Okay.
No, it should not be a minus sign because the above line.
Yeah, there should not be the minus sign.
Yeah, in the above line.
In the minus G not
In
there.
yeah. Okay, so that's what I was. Okay, good. This shouldn't be a minus sign, and therefore there is
Yeah,
no.
yeah.
This equation is correct. This equation is wrong. Thank you. Yeah. So suppose the observer A sends two light pulses. Okay, and the first pulse is sent at time say t1, and the second pulse is sent at time t1 plus delta ta. Okay, we want to ask a question: what is the duration separation between those two uh, of, uh, light pulses when the observer B measures it? Okay, so observer sees that the interval between those two is delta TB. Okay, then the time taken by the pulse 1 to travel from A to B, okay, would be uh, T1B minus T1A. This one stands for the first pulse, okay, and that is just integrating this quantity from RA to RB. Okay, so I shouldn't have a minus sign here. Okay, so okay. Similarly, you could have done the same thing with the second pulse, and it should be T2 B minus T2A, okay, to be this integral. Okay, yeah, so it should be T2A actually. Okay, but the point is that, like, this, since the metric is static, this time T1b minus T1a should be same as T2b minus T2a, right? Because the time is not going to change because the metric is independent of time. Okay, so therefore you you find that T2a minus T1a should be equal to T2b minus T1b. Okay, which is the same statement as delta Ta is equal to delta Tb. Okay, but now let's ask this question from the proper time point of view. Okay, and that's where the differences would occur. Okay, so from the proper time point of view, delta tau a is equal to minus g00 to the half times delta Ta, whereas delta tau b is equal to minus g00 at Rb to the half times delta Tb. Now delta Ta is equal to delta Tb, but g00 at Ra is not equal to g00 at Rb. Okay, and therefore delta tau a upon delta tau b, or the other way around, delta tau b upon delta tau a can therefore be written as square root of g00 at Rb by square root of g00 at Ra. Okay, but this quantity delta tau b is kind of a frequency, right? Because what are we doing? We are sending two pulses at which are separated by some time interval. Okay, so if you are asking what is the rate at which the pulses are being sent, okay, then inverse of that would be a frequency, right? So therefore delta tau b is like 1 over omega b. Okay, so that is why this expression can be just inverted and written as omega a upon omega b is equal to square root of minus g00 at Rb upon square root of minus g00 at Ra. Okay, that is a statement that we made some time ago, that omega a upon omega b is equal to g00 at Rb upon g00 at Ra. Okay, square root of that. Okay, so now this effect is actually measurable. So unlike the earlier discussion was that the clocks would run slower or faster depending upon what's the g00 value at a particular position. Okay, at a single point there is no way of knowing it, because effectively you can always kind of convert the small neighborhood around that point into special relativistic setup, and there is nothing which you can really measure out there. Okay, but if you compare them at two different locations, then there is observable effect. Okay, so let's try to understand uh, how we understand this particular result. Okay, fine. So let's consider two static observers, OA and OB, whose velocities are UA alpha and UB alpha. Okay, these are four velocities. So if the observer is static, then its spatial components of the velocities would vanish. Only temporal component of the velocity would be non-zero. Okay. Now suppose the observer A emits the light at point PA, and that is received by the observer B at point PB. Okay, then what we can do is we can use the geometrical optics approximation to determine how these uh, frequencies that are measured can be related. Okay, so first thing is, of course, that the light would follow the null geodesic. Okay, and uh, and let's define a tangent to the null geodesic, and let's call it that to be k alpha. Okay, so since it's a tangent to the null geodesic, this is actually a null vector. Okay, k alpha would be just zero. Okay, then the frequency of emission, uh, say omega a, is k alpha u alpha a at point p. Okay, whereas the frequency which is received uh, at point B would be omega B, which is k alpha u alpha B at point PB. Okay, that is how the frequency is related to the tangents defined to a null geodesic. Okay, so let's try to understand this a little better. Okay, so first of all, UA and UB are the unit tangents to the geodesic. Okay, and therefore we can write them in terms of time-like killing vectors. The reason why I want to look at time-like killing vectors is because we are looking at the geodesics and we are looking at the observers who are static. So the geodesic would be time-like actually. Okay. So, so you can write down these unit vectors in terms of the time-like killing vector field as u alpha a as xi alpha upon the square root of the norm of the killing vector at point PA, whereas u alpha b would be xi alpha upon the norm of xi, sorry, to the half here at point PB. Okay, so let's try to see how we understand these quantities. Okay, from the way the killing vectors and the velocity vectors behave. Okay, so suppose xi alpha is a killing vector field, and let gamma be a geodesic with u alpha being a tangent to it. Okay, that velocity vector is always tangent to the geodesic at a given at any point, right? So then one can show that xi alpha u alpha is constant all along the geodesic. Okay, and that's not very difficult to see. To see this, let's just ask how does the combination psi alpha u alpha vary as we move along the geodesic. Okay, so so as you change the point on the geodesic, then xi alpha u alpha would be modified by u beta times del beta acting on xi alpha u alpha. Okay, this is a statement of the rate at which a particular quantity would change along the geodesic. Okay, so what you could do is you can take this covariant derivative and take it through. Okay, so either it would act on xi alpha or it would act on u. Okay, so you get these two terms, and you can see that both these terms actually vanish individually. First term vanishes because u alpha u beta is symmetric. Okay, and therefore you can symmetrize this, and you can write this as half of delta beta xi alpha minus delta alpha xi beta, but xi is a killing vector, so that symmetrized version of that would be 0 because killing vector satisfy that equation. Okay. On the other hand, second equation is second term vanishes because u is a tangent vector to a geodesic and therefore should satisfy geodesic equation. Okay. So to see that this u beta uh, del beta of u alpha is equal to the geodesic equation, let's try to kind of expand this quantity. Okay. So first thing is that like u alpha itself is like dx alpha by d lambda. That's what we mean by velocity. Okay. So just a second. Okay. So so let's substitute this quantity inside this u beta del beta u alpha equation. So that can be written as u beta partial beta of u alpha plus gamma alpha beta gamma times u beta u gamma. That's what this covariant derivative would mean. Okay. Now u beta del beta itself is same as the derivative with respect to the proper uh, uh, either you call it proper time or you call it uh, the variable which defines the geodesic. I mean measures the geodesic length. Okay. So you can convert this u beta del beta as just dd lambda. Okay. So therefore, this quantity can be written as dd lambda of u alpha, and this quantity is gamma alpha beta gamma times u beta u gamma. Okay. But that's precisely the geodesic equation. Okay. So therefore, if u beta is actually tangent to the geodesic, then it satisfies the geodesic equation. And therefore, what we find is that variation of xi alpha u alpha along the geodesic, okay, just vanishes. Okay, in other words, xi alpha u alpha is constant along the geodesic. Okay, because the first term vanishes due to killing vector equation, and the second term vanishes due to geodesic equation condition. Okay, So we will use this fact that xi alpha u alpha is constant along the geodesic to understand how these frequencies would change. Okay. Now notice that for a null geodesic, k alpha that we had defined earlier was tangent. Okay. So so we have defined that the tangent to the null geodesic be k alpha. Okay. So k alpha was the tangent to the null geodesic. Okay. So therefore xi alpha k alpha would be constant along the null geodesic, exactly by this small digression that we had, right? That xi alpha u alpha is constant along the geodesic. Along the null geodesic, xi alpha k alpha would be constant. Okay. So that tells us that xi alpha k alpha at PA should be equal to xi alpha k alpha at PB. Okay. Now we have omega A upon omega B, which is written as k alpha u alpha at PA upon k alpha u alpha at PB. Okay. So what we could do is you go back and use the definition of u alpha, okay, written in this particular form. Okay. So so we substitute u alpha as xi upon the norm of xi to the half, which is written out here. So you get a k alpha xi alpha upon norm of xi to the half at PA divided by k alpha xi alpha at PB times the norm of xi at PB. Okay, that is how omega A upon omega B would be. Okay, but in this expression, the first ratio is constant because that just gives you 1. Okay, so therefore omega A upon omega B is just a second ratio. Okay, which is the norm of xi B at PB divided by norm of xi B at PA. Okay, but we know what these are. Remember, they are time-like killing vectors. Okay, so therefore that factor is just the G00 to the half. Okay, so therefore 1 minus 2 gm upon Rb divided by 1 minus 2 gm upon Ra whole to the half. Okay, this of course is used for from the fact that we are studying this whole problem in the short sheet geometry. Okay, fine. So now this clearly tells us that the frequency emitted at point omega A and frequency measured, at point A and the frequency measured at point B are quite different simply because these factors are not same. Okay. For example, if RB is larger than RA, okay, that means if the emitter is closer to the massive body and the receiver is away from the massive body, then omega B would be less than omega A. Okay. So omega if A is closer to the body, then omega is larger than omega B. Okay. Now, if omega B is smaller than omega A, then the light emitted from point A, okay, would have, when it is measured at omega B, would have reduced frequency. Okay, and that is the reason why it is called gravitational redshift. Okay. Now, if you really think about it intuitively, this is kind of obvious in the sense that, like, if you are looking at the gravitational potential in a very simplified kind of non-relativistic fashion, that the potential is going down as 1 over r, okay, rather minus 1 over r, then for a smaller value of r, okay, if you have a particular frequency, then that frequency would be an energy available above the gravitational potential, but the gravitational potential has fallen quite a lot. So the energy available is large at small r, okay, but when it is emitted, large amount of energy of that would be actually spent in overcoming the gravitational potential itself. Okay, and therefore in the process of reaching at larger values of r, the photon would lose its energy in overcoming the gravitational potential, and therefore the frequency measured at large distances is smaller than the frequency emitted at smaller values of r. Okay, so in that sense, intuitively, you would have expected that if RA is smaller than RB, then omega A would be larger than omega B. Okay, does that make sense? Okay, so there is a complementary way of looking at the gravitational redshift, and to understand that, let's work again in the Schwarzschild geometry. Okay, so and what we'll do is that we'll basically use the fact that in the neighborhood of any point, ordinary point in the Schwarzschild geometry, we should be able to use a special relativistic formulation. Okay, which is a statement of equivalence principle. Okay, now if that is the case, then the hydrogen atom spectrum at any given point would be identical to the hydrogen atom spectrum that we measure in the lab. Okay, now the hydrogen atom spectrum that we measure in the lab is in the local coordinate system, and therefore it's in the Minkowski space, and we know what that spectrum is. Okay, now let's imagine we are looking at a particular transition. Okay, say from a third excited state to second excited state. Okay, nothing very special about it. Only choice is to ensure that the light emitted is visible. Okay, Balmer series is visible light. So it can be emitted from any excited state to second excited state would be a visible light. If it goes to the ground state, then that light is in ultraviolet. Okay, one can measure it, but may not be able to see it. Yeah, is that a question? Was that a question?
No, sir.
No. Okay. Okay, so suppose we consider that RB is much larger than RA. Okay, and RB receives a light emitted by this hydrogen atom transition that actually occurs at RA. Okay, so RA is small, so it's closer to that massive body which has produced the gravitational, produced the curved space-time, and RB is very far away from that massive body. Okay, now as we have seen that the frequency measured by the observer at RB would be less than the frequency emitted at RA. Okay, which is that formula that we just looked at. Okay. Omega A upon omega B is this 1 minus 2 gm upon RB upon 1 minus 2 gm by RA whole to the half. Okay. So therefore, the observer B will therefore conclude that the frequencies at RA are redshifted with respect to what he has. Okay. Why is he concluding this? Because n equals 3 to n equals 2 transition energy that the observer B would measure would be the energy difference between these two in the Minkowski space approximation in the neighborhood of RB. That energy difference is large compared to the energy difference that would be measured by the light emitted at RA and received at RB because of the redshift. Okay, fine. So therefore, it would appear, that the observer who is very far away from this massive body, okay, would claim that as you go closer and closer to the massive body, you see that there is redshift occurring. Okay, is the point clear? Let's put it a little differently. Suppose you want to get the same spectrum that the observer at point B measures, okay, for n equals 3 to n equals 2 transition, the frequency at R equals RA should be much larger. Okay, it should be much larger than the energy difference between this. Okay, so only if that happens that the observer B would measure the same frequency that he or she would measure from n equals 3 to n equals 2 transition. So in reality, the amount of energy that one needs to spend at RA, when RA is smaller than RB, is larger than the amount of energy you need to spend for this transition at RB. Okay, but nevertheless, the observer at RB would conclude that the gravitational redshift is occurring at RA. Okay, because the measurement seems to show lower frequency. Okay, good. So what happens is that as you start going to smaller and smaller values of RA, the observer who is sitting very far away would see the spectrum more and more redshifted. Okay, fine. So therefore, you may find a point at which the amount of redshift could just become infinite. Okay, and that's not very difficult to figure out as to where that would happen. Okay, so if you go back to this formula and you want to ask what is the point at which the redshift would become infinite, okay, that would tell you that that would happen when this quantity becomes zero. Okay, and that just tells you that if RA is equal to 2 GM, okay, then this quantity vanishes. Okay, but RA is equal to 2 GM is what's called the horizon. Okay, so horizon in the case of short shell geometry also turns out to be a surface of infinite redshift. Okay, now I should warn you that this is a feature that only a certain class of black holes have. Okay, that for example, short shell. I haven't said that short shell solution is a black hole, but I'm sure you already know this. That the short shell solution has the horizon uh, being an infinite redshift point, as well as the horizon being the point at which you have what is it called? The time dilates to infinity in that case. Okay, so therefore, now these two things don't have to be same. But if you go back to the short shell solution, uh, give me a minute. Yeah, if you go back to the short shell solution, you'll notice that the GTT factor and GRR factor are essentially same functions, inverse of each other, but the same functions. So therefore, when this quantity vanishes, this quantity diverges. Okay, fine. But not all solutions to Einstein uh, equation due to point masses are of this kind. Okay, for example, if you look at a solution, this is what is called a short shell solution. If you look at a solution which carries charge, okay, that solution is called Reissner-Nordstrom solution. That also has similar feature. The GTT factor and GRR factor are inverse of each other. But if you say that, like, besides having a charge, if the particle, if that particle is actually rotating, okay, then which is called a rotating solution. In that case, this component and this component are actually not the same. So therefore, the infinite redshift point is different from the location at which the horizon is. Okay, so horizon location is different from the location of infinite redshift point. It has very interesting implications. There are things like Penrose process or something which can happen in those kind of solutions where you can lower some object into this solution, and it crosses the infinite redshift point but doesn't cross the horizon, and then you can pull it out and you can actually pull out energy from solutions of this kind, which is what is called a Penrose process. Okay, uh, which of course you wouldn't be able to do in, say, short shell or Reissner-Nordstrom type of solutions, in which the infinite redshift points and the horizon are identical. Okay. So far we have looked at effects of time clicking at different rate at different values of row. Okay. Now what we could do is that instead of looking at time clicking at the different location, we could just set delta t to 0. Okay. Then you will find that the spatial part of the line element basically reduces to only the radial part of the line element. Okay. And this radial part of the line element, because 1 minus 2gm upon rho is sitting in the denominator, okay, would always have a larger value than d rho square for any finite value of rho. D rho square is, of course, part of this kind of metric only when rho is equal to infinity. So asymptotically, you get d rho square. Okay. Okay. So what does this mean? By this we mean that if you did not have this 1 minus 2gm upon rho inverse factor sitting in front of d rho squared, then the spheres, I mean, we are looking at fixed theta and phi, but like suppose you allow changing theta and phi, hold dt equals 0, then different rate values of rho would correspond to different spheres, and the different spheres would have radius determined by rho itself. Okay. But because one because d rho square is multiplied by 1 minus 2gm by rho inverse, okay, the proper radial distance in fact is larger than the coordinate radial distance. Okay. So therefore, if you take two concentric spheres, one with radius rho and another with radius rho plus d rho, you would have thought that the difference between these two is just d rho. But that's not true. Because of this factor, the uh, fact, actual distance, radial distance between them is d rho upon 1 minus 2gm by rho. Okay. So it's kind of hard to draw this in a plane simply because if d rho squared had no factor sitting in front of it, then you would have just drawn them to be concentric circles or concentric spheres. Okay. But because this factor is sitting around, you cannot even draw them as concentric spheres. Okay. Now, of course, as I said, that if you take rho very large, then this quantity really asymptotes to flat space. Okay. Because for very large rho, 2gm upon rho can be ignored, and then this becomes just d rho squared. Okay. And that's like a flat space. Okay.
Sir,
yes.
there should be a square root in this d rho over 1 minus.
Oh, here, no?
Yes, sir.
In this, yes. Yeah, you're right. Thanks. My handwritten notes are just too many typos, actually. When I was typing them from my handwritten notes, I was at least eliminating few of them, although typing has its own typos, but at least, yeah, should put half. But I will use it correctly. I wouldn't use this way. I think as you go down, you can see this d rho upon 1 minus 2gm by rho to the half. Okay, so we want to actually compute the distance between two spheres, one of radius rho and the other rho 1 and other radius rho 2. If the space was flat, then you would have drawn them just like this. Okay, the modular quality of my drawing, these are two concentric spheres. Okay, and you would have said that the distance between them is just rho 1 minus rho 2. Okay, modulus of it, if doesn't matter which one was bigger then. Okay, but because the metric is like this, okay, the distance between them is actually obtained by integrating this quantity. So you have to take d rho upon 1 minus 2gm by rho to the half. Okay, and integrate from rho 2 to rho 1. Okay. So let's take rho to be sufficiently large so that we can expand this quantity. Okay, and just try to get a picture of what it is doing. Okay. So by sufficiently large, I don't mean that you have to take very large quantity. As long as this quantity is larger than 2gm, that means you are outside the horizon. That's good enough. Okay. So if you do that, then you write down this, expand this denominator and write that as 1 plus gm upon rho plus other terms. Now you can integrate. D rho just gives you rho 1 minus rho 2, and d rho gm upon rho would give you gm times log of rho 1 by rho 2. Clearly, this quantity is larger than rho 1 minus rho 2 because this is positive. Okay, this is positive because we have taken rho 1 larger than rho 2. Okay. Fine. Now to depict this, it is better to draw the picture not in this fashion of drawing concentric circles or spheres, but to draw one sphere like this and another sphere like that downstairs. So the geometry, curved geometry, is actually kind of making the sphere at rho 2 occur at larger distance away from the sphere at rho 1 than what you would have thought in the flat space. So this upper picture would part of the picture would look like flat space, but the real picture is actually following this curved line, telling you about how the spheres, concentric spheres, are separated by larger distance than the difference in the radii. Okay, so there is a way of kind of making it a little more pronounced by doing a change of variables. And to do that, let's do the following change of variable. Let's write down rho is equal to r times 1 plus gm upon 2r whole square. Okay, so this is just some general coordinate transformation which will make this expression look a little more pronounced. So let's put this back in the metric. So to do that, let's write down d rho. So d rho would have a contribution from first term, which will be dr times 1 plus gm upon 2r whole square. The second term is when this varies, and that is r times 2 times 1 plus gm by 2r minus gm upon 2r squared times dr. Okay, so you can kind of massage this expression and check that you can write this as dr into 1 plus gm upon 2r times 1 minus gm upon 2r. Doesn't look obvious, but if you stare at it for a minute, you'll see it. Okay, so 1 plus gm upon 2r can be taken common, so you can take that factor out. Then you have 1 plus gm upon 2r coming from here, and this thing with 2 times r cancelling 2r here, this is minus gm upon r. So 1 plus gm upon 2r minus gm upon r is 1 minus gm upon 2r. Okay, so that's how this expression comes about. Okay, now the other term that we have to worry about is this piece to the half, but this term. So 1 minus 2 gm upon rho. But rho is written in terms of r in this particular fashion, so you plug it up there. And that looks like 1 minus 2 gm upon r times 1 plus gm upon 2r whole square. Okay, so that you can kind of manipulate a bit and write that as 1 over 1 plus gm upon 2r squared. That's take it common. Then this factor goes in the numerator, which is 1 minus gm upon 2r whole squared minus 2 gm upon r. Okay. Now you can check this expression itself is 1 minus gm upon 2r whole squared. Okay. So therefore, what you get is the result of this type 1 minus gm upon 2r whole squared upon 1 plus gm upon 2r whole squared. That is what this quantity is. Okay. So once you do that, then you put it back in the metric. 1 minus 2 gm upon rho occurs in the numerator for dt squared, in the denominator for dr squared. Okay. So let's plug it in. This is d tau squared is equal to minus 1 minus gm upon 2r whole squared upon 1 plus gm upon 2r whole squared dt squared plus the other way around term for dr squared. Okay, this quantity in the denominator, this in the numerator. Okay, times dr squared is coming from d rho squared, so this quantity squared. So there it is, dr squared times 1 plus 2 gm upon r whole squared, 1 minus 2 gm upon r whole squared, times rho squared d omega squared would become r squared times 1 plus gm upon 2r whole to the 4, because of the square here. Okay, d omega squared. Okay, so let's keep the dt squared as it is, but dr squared and d omega squared can be simplified. First thing is that 1 minus gm upon 2r whole squared cancels. 1 plus gm upon 2r whole squared goes to the fourth power in both places. So you can pull that out, and dr squared times r squared d omega squared. Okay. Now the reason why this makes it pronounced is the following: that if you set dt equals 0, okay, then you can see that the concentric spheres that you're looking at for the radius difference to be dr are given by the factor 1 plus gm upon 2r whole to the fourth. Okay. So clearly the distance between r1 and r2 concentric spheres with radius r1 and r2 is much more than just mod of r2 minus r1. Okay. Fine. So maybe I'll stop at this point. We can kind of resume at this point next week. Is that okay?
Sir, I have some things to ask you regarding that paper you sent me.
Which paper?
Regarding the project.
Oh yeah, sure.
Yeah, sir. Can I share my screen then?
Yeah, just hold on.